Bem-vindos ao nosso espaço, um mergulho profundo nos assuntos mais interessantes de esportes, ciências e temas gerais do momento. Aqui você vai encontrar conteúdo de qualidade, com análises empolgantes e descobertas fascinantes que vão expandir seus horizontes. Nossa missão é trazer informação relevante de forma dinâmica e descontraída. Queremos que você faça parte dessa jornada incrível de conhecimento e diversão. Se gostar do nosso conteúdo, não esqueça de deixar seu like e se inscrever no canal para não perder nenhuma novidade. Ative o sininho também. Aproveite!
If you love science, don't forget to like and subscribe. When a massive star dies, it doesn't just flicker out, it rips itself apart in a cataclysmic blast we call a supernova. This event is the universe's ultimate recycling program. It's a moment of furious, blinding energy where elements heavier than iron, including the gold in your jewelry and the silicon in your computer chips, are forged and then violently scattered across interstellar space. What remains is a churning, chaotic cloud of superheated plasma known as a supernova remnant. This remnant is the raw material for the next generation of stars and, eventually, planets like Earth. But how does this chaos turn into order? How does this extremely hot, turbulent gas structure itself into the dense, cool molecular clouds necessary for stellar nurseries? The secret, it turns out, lies with the most unsociable elements in the periodic table, the noble gases. And perhaps the most surprising regulator in this cosmic debris field is xenon. We usually think of noble gases, like neon, argon, and xenon, as being totally inert. They are the chemical loners. They don't bond, they don't react, and they seem to prefer remaining invisible. In the chemistry of our world, they are footnotes. But in the violent thermodynamics of a supernova remnant, their physical properties, specifically their refusal to engage in electron exchange, make them profoundly powerful. They are the shadows that structure the light. When the supernova shockwave dissipates, the debris cloud is incredibly hot, millions of degrees Kelvin. It is a plasma, where electrons have been stripped from their parent atoms. This plasma needs to cool down drastically to condense into usable matter. Cooling in such environments is complex, often relying on radiation generated when electrons recombine with ions. This recombination process is critically sensitive to the charge state and the atomic mass of the elements involved. Enter xenon. Xenon is exceedingly heavy, boasting an atomic weight of 131. It is far heavier than the hydrogen and helium that make up the bulk of the cloud, and even significantly heavier than carbon, oxygen, or silicon. More importantly, xenon has an extremely high ionization potential. In simpler terms, it takes a massive amount of energy to strip xenon of its electrons, meaning xenon atoms resist becoming fully ionized compared to lighter, more chemically active elements in the same thermal environment. Imagine the turbulent, super-fast flow of the supernova debris. Lighter ions are moving erratically, colliding and constantly changing their charge state. The xenon atoms, however, act like heavy, non-reactive anchors. Their inertia resists being swept up easily by the flow, and because they tend to hold onto their electrons longer, they don't participate in the complex radiative cooling chains in the same way other elements do. By remaining dynamically distinct and chemically isolated, xenon alters the physics of turbulence and fragmentation within the cooling nebula. It doesn't just passively exist, it influences the momentum transfer across the remnant. This drag and inertial resistance affects the critical mass required for the gas to become thermally unstable and fragment. If cooling happens too quickly and uniformly, you might get small, unstable clumps. But the presence of these heavy, stable xenon atoms modifies the characteristic length scale of density perturbations. Essentially, xenon helps define the size and structure of the resulting gas filaments and clouds. By regulating the dissipation of energy and the clumping process, xenon dictates the density fluctuations that are necessary seeds for future molecular clouds. Without this invisible, inertial regulation provided by noble gases, the debris clouds might disperse too rapidly, or fragment into clumps that are too small or unstable to ever form stable stellar systems. This principle isn't just theoretical. Astrophysicists utilize isotopic signatures found in ancient meteorites, material formed very early in the solar system's history, to trace the presence and influence of heavy, non-reactive elements like xenon and krypton. These traces confirm that these noble gases were present in the forming nebula and that they bear the telltale signs of processing through a high-energy supernova shockwave. Their specific ratios suggest they acted as stable checkpoints during the turbulent phase of elemental condensation. So, the next time you marvel at a breathtaking nebula, remember that the beautiful structure you see, the sculpted pillars and the dense cores, may not just be the result of gravity and light elements. It might be subtly regulated by the quiet, heavy presence of xenon, the silent element casting its shadow across cosmic recycling, ensuring that the death of one star truly leads to the birth of the next. For more incredible facts like this, don't forget to subscribe and turn on notifications.